Welcome. I'm Alessandro Amici. As a day job, I'm CTO at Biopen, a small company in Rome. And we work with scientific computing, scientific data, especially satellite and so on. And this is the reason we have met the scientific ecosystem. And in particular, we like very much what dask is doing right now. So let's start with scientific data. Usually, the point about scientific data is that it can be big. So, and computing can be long. So let's start with a little bit of vocabulary about data size. And computing power needs. So first of all, about data size. We will call in the way I think of it and the way I will use in this talk is that small data is something that fits in RAM. It's easy. You don't need to do much thought because you use the standard things. Medium-sized data is where things start to be interesting because it fits usually in your storage, so you have the data in your machine, but it doesn't fit everything into RAM, especially during computation time. So you need to start doing tricks because you cannot go straight forward with load data, process it, save it. And then there is this concept of big data where it doesn't even fit your storage. So you need really to use distributed storage and then distributed computing and so on. By computing power, the main point, the classification, the easy classification is that you can use synchronous computing where just one single core is enough. This is whenever you're testing, it's usually fair. If you go and want to do something more complicated, especially with more data, you want to use parallel computing, at least multi-core, and on a single machine. This is the first level of complexity. Using efficiently multi-core on a single machine is already quite a challenge. And the next level is when you want to go distributed. So you want to use multiple machines and possibly multiple cores. Usually, small goes with synchronous. Usually, small you like to have parallel as well. But medium almost always goes with parallel because data starts to be big, starts to grow, and big data usually goes with distributed. So in this case, I will usually refer to data size and not to the other. The main point about big data is buy access to bigger machines, because this is everything about what fits in the memory of the machine that you are using at that moment. If technically it would fit another machine, but not yours, you cannot work, and you need to do more complex things. And right now, access to a machine, not really buy a machine, but buying access to a machine is rather easy. That is, you can actually buy machines with terabytes of RAM on Amazon, or at least buy time. So most of the big data problems, if they're not really big, or not most, but a lot of big data problems can really be solved more efficiently by bigger machines. But this is not always the case. In particular, scientific data, there are some fields where whatever RAM you have, you want more, simply because you get better results if you use more RAM. The first we've heard, it's the data analytics, data science, data analytics, which we have heard in the previous keynotes. It's mostly finance, research and development, analytics, usually business intelligence and so on. They're based on records, so you have items with very different data types. And prevalent technologies are R, Java. You can use Hadoop, Spark, depending on the level of complexity that you want to treat, how big and distributed is your data and processing. Then there is the part that I'm more familiar with, that is scientific computing. This happens in physics, engineering, biology, and everything that uses something that describes the world in 3 dimensions. So it's based not on records, but on hypercubes. So if you want to describe the whole atmosphere of the Earth, you need to have a hypercube, a cube with latitude, longitude, and height, and time, and possibly another time, and a lot of things. In this case, prevalent technologies are low-level stuff like Fortran, C, and C++, in some cases MATLAB, and you go to the distributed part using high-performance computing and MPI, message passing interfaces. So quite a different set of technologies with respect to the first part, but these are everything that is outside of Python. So what is the key features of these kind of technologies? Clearly, a lot of them are, the key is to be fast at computing. So you have fast runtime, C, C++, Fortran even. The main advantage is speed. But also they are memory efficient data types. So this is very important for treating, to move your big data problems to a small data. If you have a more efficient data structure, you can actually use one machine and possibly one single thread instead of several. But still, it's very useful when you have when you go to the big stuff because you need less machines. They also need to have. They also have, and this is the reason they thrive, mature ecosystems and communities. In particular, a lot of dedicated tools and libraries and tools specific to distributed computing of big data, like MPI and Hadoop and Spark. Now, the point is how Python is even a contender in this field, since the people coming from outside Python just say Python is slow and things are too big, etc. So fast computing. Right now, it is obvious that if you use the standard interpreter for doing this kind of stuff, it's really too slow because it's interpreter and it doesn't have a JIT compiler. At least not the standard Python. You need to go to other distribution like PyPy. But even more, it doesn't have memory efficient data types because all native types are rather big and they are garbage collected. So you don't have much control on when data is removed. You know when it is created, but not when it is removed. But, and this is where things start to get interesting, we do have a mature ecosystem and communities, especially in dedicated tools and libraries. They are thrived, NumPy, Pandas, Xarray, and dask. It's the things that I use the most, but there are several others. And there are options for distributed computing. We will talk about dask distributed now, but Airflow, Celery, and others are also. So let's see where all the technology get in so that we know what is the role of dask. So in small scientific data, it's all about data structure and bindings to low-level stuff. The heroes here are NumPy and the array and Pandas data frame. They are C-level data types, and they have C-level methods. It means that they present a compact representation of data in memory. So it's not the standard data types that are big, but these are more or less not much bigger than equivalent data types for C or C++ or Fortran. They provide also high-level view classes so that you don't need to copy data too much. Fast C-level computations for all the operations. And the most important point is that there are tons of efficient tools, including binding to most of the C and C++ and Fortran libraries. In Python, the key to get performance is not to do the for loop in Python, but to get someone else, some libraries to do the work for you, the dirty work for you. You just do the high-level composition. Still, there are remaining issues if you want to use Python in scientific data, even if you use at the best your ND arrays, and your data frames. First, there's no support there's no native support for parallel execution, and we know parallel execution, it's a bit tricky with Python because of the GIL for multi-threading, then you need to use multi-processing. This is one of the things that we are going to address in this talk. And then the real issue with Python is that there are a lot of copies in RAM, and again, the garbage collector kicks in also with the nice data types, because you don't control when data disappears. You don't need the data anymore, but maybe it stays for a few instructions before it is removed. And that is copied a lot. This is the real point. in real life, you will hit the out-of-memory killer more often than the too slow or timeout on your queue system. So when used properly, Python is not that slow because operations are done in C. But in it, it needs explicit parallelism, and it is a memory hog. So in order to go to the next step, to medium scientific data, especially the memory part, it's really the key. So enter dask. Dask is a flexible library for parallel computing. Go to dask.org if you want to know more. It is mostly has been written by Matthew Rocklin, who worked at Anaconda, but now has been hired by NVIDIA, explicitly to work on open source code. So it's really thriving, Dask, at the moment. And in this case, the key in going to parallel and to memory management is about blocks and tasks. So Dask provide scalable block-based data types, which are very similar to the standard NumPy ND array and pandas data frame. They are called Dask array and Dask data frame. And it provides block-based operations for all of them. So it mimics most of the interface of array, of the NumPy array and data frames. And a lot of the methods have been ported to use block-based operation. So the idea is that all operations are divided into, also your data is divided into blocks, and operations are done to combine, to process operations that are either on a single block or combine the value in several blocks. All the operations become tasks, so that there is a task graph that is a description of what is going to happen. And the Dask also provide optimization for the task graph and dynamic task scheduling. So blocks, a map of what needs to be done with these blocks, and the way to do the operation when it's needed. You have configurable schedulers, so that, for example, you can go from synchronous to distributed, just switching knobs. And most importantly, you have lazy and parallel computation. Since now you have a workflow and a scheduler, you can try to use both all your CPUs, all your cores, and we will see later, all your machines. Just to have an idea of the underlying implementation, a Dask array is actually a superstructure on top of NumPy arrays. You have blocks, possibly complex segmentation of your array, and at lower level you have just NumPy arrays. With Dask, it's basically the same. You have a division along your index, and you have pandas data frames that are just glued together by the Dask data frame. Once you want to do, for example, a simple operation, you just create the ones, and then you want to do a sum. What happens behind the scene is that all data creation and access is done in blocks. After that, operations that are just just a single block is needed are performed on that block, and so they can be parallelized. When you need the result of several blocks, you have the scheduler that just waits for all the useful work to have finished, and then it combines the result in an operation and gives you the result. Now this is basically the simplest interesting workflow where you have basically MapReduce. You map your data, process them, and then merge them. But Dask with respect to other technologies, dask is not really tied to this kind of behavior. It's really a much more generic tool that builds arbitrary complex graph. So, for example, this operation here, it's a dot product of a sum, and then you add mean and compute a standard deviation. And this is the whole graph that appears in the task graph that is built by dask and is performed and is crunched at runtime. One of the extremely important points when you work with dask is that computation are lazy, which means if you need a certain block in a computation, if you need, for example, this block here, all the things that needs to be done to reach here are performed, but not anything that is outside of the tree. So typically, operation happen when you get out of the dask environment. As long as you use dask-aware operations, what happens is just this graph grows and grows, but no real computation is done, or some computations are done, but not the heavy ones. At some point, transparently, some piece of your code will ask for the real values of a certain piece, and at that point, the scheduler starts. It's quite surprising sometimes, because you think that everything is going very fast, and then you try to plot something, and then you wait for 20 seconds, because that is where the real computation is happening. So, task schedulers is here on the right. They are pluggable. It means once you have your data structures, the operations build the graph, and then the graph needs to be actually computed. In this case, you have several choices. For example, synchronous is the single core one. It's very useful for testing, so you check that if you have a problem, you can test if it's in the scheduler or actually in your code. Threaded and multiprocessing go for multi-core and single machine, so we are in the intermediate step in processing. Threaded, obviously, it's not very useful in Python, or at least it has very specific use cases. Multiprocessing is much more general. It works pretty well, and it's very transparent. That is, you can just switch the scheduler, and you get faster stuff, your computation faster. Not always. There are always asterisks, but it works quite well. And then we would see just later, you can go distributed with just by switching again the scheduler, connecting to a cluster, and then you can ship the actual processing outside. Let's see dask in action. This is a rather big computation, and among the other things, dask gives you a few applications to see what's going on, and they are quite nice. Unfortunately, the graph began really big, and really confused quite fast, especially for the things that I do. So it's not easy, but you can see where things are blocked. You have running, and you see that there are several roads that are taken, and then you get your final result. What's the magic of dask? So, as a developer, what is that you notice and you want and you try to achieve? So, first of all, the dask data types implement native protocols. It means that they feel very much like the originals. And if you use the dask data types as the original, that is, you don't use the dask sum, but you sum with NumPy, what happens is that transparently, you get the computation and an NumPy array as a result, so you don't need to explicitly get out of the multiprocessing environment. It's transparent. This means that, for example, matplotlib works as it is. So matplotlib basically doesn't know that if it is plotting a NumPy array or a pandas array, it just plots it, and it works. You have block-based operation and data access. This means that especially in the distributed case, you want to have a distributed file system where all the nodes look at the same data and can just get a piece of the data out of the data sets. Dask-aware code only builds the graph as it runs, and it only getting out of Dask triggers the computation. And the computation is triggered only for the piece of the graph that is needed for that particular part. There are cases where this is tricky because there is a cache. So if you already computed a piece of a result, it is in memory for some times, but can get out. But the cache, it's removed at some times. So if you do the operation in the awkward order, you can end up doing the same computation twice. There are knobs that you can tune if you know that this is happening. But this is one of the actual downside of doing lazy operations. So as I said, tuning knobs are there, but also monitoring tools. Now, the real key, the real magic is that if you look at the code with NumPy and with Dask, unless you go and turn the knob, it's mostly the same. So you have some different import, and that's it. Now, what happens if you go one step? How Dask and distributed in particular help you going one step further? Dask distributed is a lightweight library for distributed computing. Now, the key here is lightweight because it's a pure Python implementation. As a matter of fact, it's similar to the thing presented by the previous speaker of the keynote, but it used a very different approach where everything is done at a very high level, that is Python level, and not using MPI, for example. This means that Dask is less efficient, but less tied to the architecture and to the, let's say, to the libraries that you have on your machines. It works with a single scheduler and many workers. So the distribution is you have one central core that knows what's going on and several workers that do the computation, but they're stupid. They keep the data and do the computation. The scheduler knows which worker has done what operation and what data is present there. It can operate in multiple clusters, but there is experimental support for multi-GPU clusters as well. So this is the reason Matthew Rocklin has been hired by NVIDIA, or at least this is supposedly a very useful way to get GPUs into the picture. And he has started doing work which is very promising. Obviously, the step is to be able to use GPUs without changing too much of the code and without knowing even that it's going to the GPU. Because again, you have to select the scheduler, say, I want the distributed scheduler with GPU, on a GPU cluster. And as long if Dask managed to get everything working, it's still experimental, that is all that is needed. There's peer-to-peer data sharing. This means that the workers can transfer data between one another. There's the central node, the scheduler, it's only for keeping track of what's happening, not for also storing data. There's data locality, so the scheduler knows that needs to ship a certain piece of work on the node that has that data. So it's quite efficient from that point of view. And there are monitoring applications, again, for distributed, which is very nice. So you can get, obviously, when things are distributed, they get very complex, very fast, especially if you have a problem. Debugging is a pain. And the more tool you, the real usefulness of a technology is when you can debug it. So very nice to have features, but the most important point is that you need to be able to debug it. Minimal code changes, again. That's the key point of using dask and dask distributed with your work, with work that you are already doing. You can easily start and see if it's worth in your use case. The service structure of Dask, it's very nice even for using on cloud services. You actually have your scheduler is the only thing that really needs to survive. So it's your pet in the pet kettle paradigm. And you need to get a machine that stays alive and doesn't go away. But with workers, you can buy spot instances of Amazon Web Services that may disappear at any time, and there's no problem. You lose the work that has been done up to that point, but that's no problem. The scheduler knows, and if the machine goes away, it reschedules the work to another worker. Obviously, the client, so you, when you have your Jupyter notebook, you connect to the scheduler, and that's the only one that you care, really. So, this case, you have distributed computing with minimal fuss. It's very easy to set up a cluster. You just need a daemon on every machine and a list of nodes that are up on the scheduler. It's very easy to start up because you need very simple code changes at the beginning. The more you start using Dask and Dask distributed, the more you try to use advanced features, and then code changes a little bit. But the barrier of entry is really low. You just say, let's try. One of the really neat thing is that somehow you start to think to the RAM of the whole cluster as the RAM that you have in your hand, because you can actually say, please make this very big array concrete, so do all the computations, but this stays distributed in the whole cluster, so the computations are done. You have the data in memory, but it's distributed not on just one machine. So I have been reported bugs where people send me logs and say, okay, I have this problem with a cluster with something like 10 terabytes of RAM across quite a few machines. Now, let's see how it works in a real-world use case. So what I do, among the other things, what I do is working with people, scientists working with climate change. So how do you know that climate has changed? You need some way to describe the past climate. You can get the climate data stories, the European Center, the European Archive of Climate Data. It's one of the things that I work on. This is the reason I know it very well. And you need to choose a reference period. So you want to change with respect to what? So you need to define a reference period and compute some reference statistics. We call it a climatology. For example, we can decide we want to know, we decide there's a reference period from 81 to 2010, and we say what is the monthly average temperature in that period. And we need to compute the difference, which is called the anomaly, with respect to the reference of some period that we are interested in. For example, we can decide to compute the monthly temperature anomaly for the year 2018. The reason this is an interesting problem is that the data here is big. So these are the various dimensions that are for this hypercube. So you start for data types, and then you have latitude, longitude, levels. It's the vertical height. and then you have time, and then you have a number of variables. So if you see kilobytes, megabyte, gigabyte, terabyte, you have something like 3 petabytes of data just for this, which is just one of the data sets that we are using for studying climate change. This is how I would compute the anomaly with X-array. X-array, it's a high level on top of NumPy. It's very nice because it's integrated with dask. So you just use the open multi-file dataset, and it uses dask automatically. And this is basically all of the code that it's needed to do that steps. You get your data, you select the reference period, you group, you do what is called a climatology. So actually, this is not monthly climatology, it's season climatology, but because I needed a smaller picture. But so for every season, winter, summer, and so on, you have the average temperature at the surface on all of the world. Then, in order to do the anomaly, you select the year you're interested in. You again compute the season mean, and then you just subtract the climatology. So that is the difference in temperature, the mean difference in temperature during summer, winter, I don't know the other names, but well, autumn and fall, yeah, fall and spring, yeah. Now, once you run this code up to here, it's very fast. It takes a few seconds because there is some computation is done, but not the real meat, which is to crunch something like, oh, that is terabytes, sorry. It's 1.3 terabytes of data. I think I didn't, oh, that's interesting. I have terabytes here. Well, anyway, it's 1.4 terabytes of data. But nothing has really happened yet. When things happen is here. Next line, you say, OK, I want to plot. I want to show the results. So now the dask knows that which data you need. You need actually all the data, so it does all the processing. It takes a while. And then you get the result. Now, just to understand, this is latitude, longitude. So Europe is somewhere here. And you see that in December, January, February, so this is winter, there's been a huge anomaly in the north, just north of Europe. So this is the above island, Iceland. And you cannot see the colors here. There's some blue here, but it's mostly shades of orange and red. In this case here, actually, above Europe, there's more of a blue region. So there's been it's slightly colder than usual. And in the other two cases, not much has happened except a very high, a higher anomaly up north. This is 8 lines of code that we have done. And with all the trickeries that dask gets you, and this is the official temperature anomaly for 2018, distributed in the European state of the climate from 2018. It comes from the same data. It's distributed by the Copernicus Climate Change Service, that is the owner of the climate data store. And as you see, this is something else. This is the mean temperature. And now this is much nicer colors, the proper projection, etc. But the data are basically the same. Big stuff. Big red stuff above Europe in the Arctic, quite cold in Russia, quite warm in Europe, and then average warm, still warm, but not that hot for the rest of it. So this is a non-trivial computation that you are trying to do. The scientists who are working, I mean, not once you know how to do it, you know it, but right now, if you use the right tools, it's really trivial. If you have a cluster and play with the cluster, the computation is even faster, so you can try and see if you can actually do research and development of terabytes of data quite easily. And this is it. So hope you enjoyed it.
So if you have some question, okay.
Thank you for the presentation. So in that example you just showed how many machines, can you give an idea of how many computational hours were used to do that?
No, it's not hours, or at least. I'm lucky because the people at the climate change service have a big cluster of machines, and they say, oh, this is nice, this dask stuff is nice, let's try it. Let's start at 80 machine and I don't know how many cores trial run, and so well, it was a few minutes, not much.
Yeah, also thank you very much. So how long does it take you to set up the worker nodes, and is there Conda installation for that? How involved was that? Can you comment on that?
I didn't do it by myself, and we have a Puppet deployment, so I guess we use that. In that case, so we have a standard Python environment that we can install easily on the machines with all the tools that we use, and we just added dask to the, no, not even, we added dask distributed because typically you need a way to orchestrate the creation of nodes and the setup of nodes. Apart from that, you just need a Python, a Conda setup or a Python interpreter with NumPy and the rest. I usually don't use Conda, but the main reason is that I'm almost always using Linux, and so most of the time just pip installing things work. But it's quite trivial.
Hi, thank you very much for your talk.
Yeah.
I was curious. Okay. How does it take to make the path resilient to failures? So the scheduling server to be resilient to failures, for example, do you know if you have to plan for a cluster, or does it clusterize by itself, or?
So the cluster part, it's very simple. So it's not the high availability stuff. Somehow, what Matthew Rocklin suggested, we met at the conference, is to have something like one machine that is your scheduler, and in that case, it's one scheduler. You don't have like redundancy and anything, but you can put your workers on a queue. So you know that you can have as many workers as the queue allow you at that moment. They connect to the scheduler, so they need a piece of configuration that says where the scheduler is. It's not automatic, but once they know okay, I dispatch you the work and I wait for it to be finished, it's automatic, and if the system is resilient with respect to the workers, they can die and nothing happens. So things are retried and they usually work.
Okay, I think we don't have enough time for other questions, so thank you so much for your speech.